So in today's video, I'm going to look at the second part of chapter 5.6, and this is really what would have led into 5.7. So if you are interested in that, I recommend you go ahead and just read through that chapter, especially if you've done differential equations. You should have seen it before. But this kind of leads into that. So if you are looking at taking that class, this is like the good basics to know before you go in. What I want to look at is the trajectories of these solutions. So seeing what happens with x0, x1, x2 and plotting those and seeing what the trajectory of this dynamical system is. Okay, seeing, does it go towards zero? Is it going to go off towards infinity? Or does it look like it may go towards zero sometimes and then go away at other times? Okay, so we want to see what actually happens in this system. So to start with, I'm just going to look at diagonal matrices. They're the easiest ones to deal with, and then I will deal with ones that have slightly different eigenvectors. But diagonal matrices always have eigenvectors 1, 0 and 0, 1. If you don't believe me, go ahead and quickly do a 2 by 2 matrix. Go ahead and find its eigenvectors and eigenvalues if it's diagonal. Okay. What you actually find for a diagonal matrix is that its eigenvalues are the entries on the diagonal and its eigenvectors are 1, 0 and 0, 1. Okay, so that's what we're going to deal with today. There are three cases that we need to look at. One of which is when the origin is an attractor. That means that it's going to go to zero. Okay, your solutions are going to go to zero. No matter what happens, you're going to zero. Okay, so the origin is an attractor. It can be a repeller, which means that everything goes away from zero, everything grows really, really large, goes towards infinity. Or it can be a saddle point, which is a mix of the two. Okay, so the three cases that we're going to look at. Okay, number one is when the origin is an attractor. Number two is when it's a repeller. And lastly is when the origin is a saddle point. Okay. So the first one I'm going to look at is when it's an attractor. So let's see what this looks like. Okay, plot several trajectories of the dynamical system the system that we've been looking at, that iterative system, where A, as I said, I'm just going to deal with diagonal matrices at the moment just to make it easier so that we can draw this out really easily. Okay. Now, this matrix A, first thing you always do, we already know, going back to what we did before. Okay. You're always going to write this solution in terms of its eigenvectors and eigenvalues. So what we want to do is find the eigenvectors and eigenvalues of A, and then we can write xk like this. Okay. So let's go ahead and do that. As I said, it's really, really easy for this one. The eigenvalues are going to be those entries on the diagonal. Okay. And the eigenvectors, you can go ahead and prove this if you want and do it exactly as we've done before. Those are the two eigenvectors, which means that the kth iteration can be written as, for some C1 and C2, it's going to be 0.9 to the k times 1, 0, plus C2, 0.6 to the k, 0, 1. Okay. As k goes towards infinity, what's going to happen to the kth iteration? What's going to happen to that x value? Well, it's going to go to 0, okay? This thing's going to go to 0 and this thing's going to go to 0 as k gets larger and larger and larger. However, 0.6 to the k is going to get to 0 or go closer to 0 faster than 0.9 to the k. So this thing here with the smaller magnitude goes to 0 faster than the thing with the slightly larger magnitude. Now, they've both got magnitude less than 1, so we know that they're both going to go to 0. The question is, how fast do they do it? And 0.6 to the k gets there faster than 0.9 to the k does. Okay? So, because of this, we know that 0 is an attractor, okay? Because both terms are going to go to 0. But we need to take into account that this term here gets there faster, okay? So we say that the greatest attraction is along the line that contains the origin and that second eigenvector, okay? That's the line that's going to go to 0 the fastest, okay? So anything in that direction, okay, you're going to go to 0 the fastest in the direction of this eigenvector on that line that goes through 0 and that eigenvector, okay? So the way that you say it is the greatest attraction is along the line through 0 and the eigenvector v2. Okay, because that's the line in which you're going to go to 0 the fastest. Okay, so whenever you get this situation where you have two eigenvalues, both of which have magnitude less than 1, you know you're going towards 0. You know that your solutions are going to go to 0. You then have to look for the eigenvalue of smallest magnitude. That is the term that's going to go to 0 fastest. So the way that you get to 0 the fastest is by going along that line that goes through the origin and the eigenvector that is associated with that eigenvalue. Okay? They actually have these drawn out. Most of these I'm not going to attempt to draw because I'm not very good at it. But if you go to figure 1 on page 306, they will show you a diagram that will show you exactly how you draw this type of thing. Okay, so if you look at figure 1 on page 306, it's right at the top. And they've drawn out what these trajectories look like. They have drawn multiple trajectories because each one of those lines represents where you've made C1 and C2 equal something different. Okay, so each time you change C1 and C2, they're just constants. Each time you change those, you're going to get a different path. Okay, but you can still plot x0, x1, x2, etc. You know that they're all going to go to 0 because we know that the origin is an attractor. Okay, question is, how do you draw it? Okay, well, we know that we get there fastest by going along that basically y axis, okay, because that contains that 0, 1 and the origin, okay? So the direction of greatest attraction is along that y axis, okay? So when you draw this, okay, you make sure that in that direction, okay, is where you're going to have the fastest rate of going to 0. If instead we had to look at, let's say, the greatest attraction was dealing with this eigenvalue here, let's say that this was like 0.4 to the k or something, and so your direction of greatest attraction was along the line that contains 0 and this eigenvector. When you drew that out, and please excuse how bad my drawing's going to be, but when you drew that out, it would be something like this. Okay, so in all directions, you're going to 0. Okay, in both directions, dealing with 1, 0 and 0, 1, you're always going to 0. But in this direction and this direction, you're going to 0 faster than you are in this direction or this direction. Okay, so that's the difference in the diagrams. So make sure that you always, when you draw it, okay, the direction of greatest attraction, okay, which contains 0 and the eigenvector where it relates to the eigenvalue of smallest magnitude, in this case with an attractor, okay, make sure in that direction is where you are going to 0 the fastest, okay? So make sure you get the drawing the right way around. So if in the direction of 0 and 1, 0, so in the direction of the line containing 0 and this eigenvector, your diagram would look like this with several other trajectories as well. But in our case, the direction of greatest attraction was through the line that contains 0 and 0, 1. So this would be the direction of greatest attraction. So that is why that diagram in figure 1 looks slightly different, because you have to go to 0 the fastest in that like y direction as opposed to the x direction. Okay. You can see it kind of like flattens off in the other direction, that's why. Okay. But just bear that in mind if you have to sketch some of these. Again, it doesn't have to be accurate. Just make sure that you can kind of sketch them. The next example, we have to look at a repeller. So, for example 2, we're going to be plotting the trajectories of the dynamical system. And this time, A is going to equal 3, 0, 0, 2. Okay? Same idea as before, you're dealing with xk plus 1 is still a xk. So you're still doing that iterative system. First eigenvalue is going to be 3. Second eigenvalue is going to be 2. First eigenvector is 1, 0. Second eigenvector is 0, 1. Same idea again, but this time when we write out our kth iteration, so it's C1, 3 to the k, 1, 0, plus C2, 2 to the k, 0, 1. Okay? In this case, you have two eigenvalues where you have magnitude greater than 1. Okay, both of them have magnitude greater than 1. That means that both of these terms are going to go off to infinity as k goes to infinity. Okay, but which one is going to go there faster? Well, obviously it's this term. 3 to the k grows faster than 2 to the k. So we know that this term is going to shoot off to infinity faster. So 3 to the k goes to infinity faster than 2 to the k goes to infinity as k goes to infinity, okay? So we know that both of these have magnitude greater than 1. Therefore, we know that the origin in this case is a repeller, okay? Because both of these terms are going to go off to infinity. Therefore, xk goes off to infinity as k goes to infinity. But we know that it's going to repel faster, okay? It's going to go away from 0 faster in the direction of the line that contains 0 and this eigenvector. So this time you're going to have the greatest repellent, okay, in this case. It's going to repel faster in the direction of the line that contains 0 and 1, 0. So it's going to look very similar to this diagram that I drew here. The only difference is that now the origin is a repeller, okay? So it's going to go away from the origin in all directions, but it's just going to go away faster in that 0, 1, 0 direction, okay? So if you look at figure 2 on page 306, they've had a similar example here, and it looks kind of like what I've drawn here, but this time all arrows are going away, okay? You can see it goes away from the origin faster along that x-axis, okay? Because that's the direction, the line that contains 0 and 1, 0, okay? That line is the x-axis. So it goes away faster in that direction, but it looks flatter, okay? It still goes away, but it looks flatter in the y direction, okay? So it still repels, it just doesn't repel as fast in that direction, okay? So figure 2 shows you exactly what that would look like, what those trajectories look like when you are dealing with a repeller where it's going to repel along that x-axis fastest. The next one is when you are dealing with a saddle point. So this next example is to plot several trajectories of the dynamical system. Again, we're dealing with xk plus 1 is equal to AXK. And this time A is going to equal 3, 0, 0, and 0.6. Okay, so your eigenvalues this time are lambda 1 is 3 and lambda 2 is 0.6. And again, your eigenvectors are going to be 1, 0 and 0, 1. Okay, so your kth iteration is going to look like this. Okay. So what does this look like? Well, you know that in this case, this term is going to go to infinity as k goes to infinity. This term is going to go to 0. Okay. So that tells us that along the line that contains 0 and 1, 0, so in the direction of the y-axis, or sorry, in the direction of the x-axis, it's going to repel away from the origin. Okay, so in the direction of the line that contains 0 and 1, 0, we know that we're going off to infinity because this term goes to infinity. But along the line that contains 0 and 0, 1, so along the y-axis, okay, along the line that contains this vector, we know that we're going to 0 because this term goes to 0 as k goes to infinity. Okay, so this time, if you look at its figure 3 on page 307, sorry, I'm making you look at a lot of diagrams so that I don't have to draw them and you don't have to understand my drawings. Figure 3 on page 307 shows what this will look like. Okay, so in this case, okay, as I said, along the direction of the x-axis, in both directions, you're going away from 0 because you know that 0 is a repeller along that line because 3 to the k goes to infinity as k goes to infinity. But along the direction of the y-axis, again in both directions, positive and negative, you're going towards 0. Okay, you're going towards 0 because 0.6 to the k goes to 0 as k goes to infinity. So along the x-axis in this case, you're going to infinity, but along the y-axis, you're going to 0. So in that direction. Okay, and that's where you get this curved situation. Again, each one of these trajectories corresponds to a different C1 and C2. That's the only difference. But again, you're plotting out those solutions. Okay. That is called a saddle point, okay, because it repels in one direction and attracts in the other direction. So when you have that situation where you've got one eigenvalue of magnitude greater than 1 and one of magnitude less than 1, you're dealing with the origin being a saddle point. Okay, so that's the third example. Okay, now I want to do an example where you don't have 1, 0 and 0, 1 as your eigenvectors, okay? I'm still going to be sticking to a standard 2 by 2 and I will tell you what the eigenvectors are. It will just look slightly different in this case. And this time I'm going to have to draw it, so please excuse my drawings. So this time you're going to have some random eigenvectors. Okay, so I'm going to say that, again, we're dealing with this dynamical system. And I'm going to take A to equal 0.5, 0.6, negative 0.3 and 1.4. Okay. If you were to work this out, and these are what your eigenvalues are, and then your eigenvectors are 1, 1 and 2, 1. Okay, without doing any work already, we know what the origin is going to be. Okay, we have one eigenvalue that has magnitude greater than 1 and one eigenvalue that has magnitude less than 1. Okay, so without doing any work, we already know that the origin is a saddle point. Okay, because we have one greater than 1 and one less than 1. So I know along the line that contains 0 and this eigenvector, I'm going to be shooting off towards infinity. But along the line that contains 0 and this eigenvector, I know I'm going towards 0 because 0.8 to the k goes to 0. So my solution Let's quickly write out our solution. Is 1.1 to the k 1 plus c2 0.8 to the k 2 1. Okay, so that's our solution. So we know in this direction we're going to infinity, and in this direction we're going to 0. So let's try and draw this. I have drawn this in the notes. Again, it may look kind of confusing because it's not easy to draw these, but you only need to do a sketch. Okay, so the line that contains 0, 1, and 1, 1 is going to look roughly like that. Okay, and then the line that contains 0 and 2, 1 is going to look like this. Okay, so they are my two lines. Now I want to look at what the trajectories look like. You should do these in the same color, but it doesn't really matter. I just want to show you what this looks like. So I know along the line that contains 0 and 1, 1, going back to our solution, I know that in this direction, I'm going to be going towards infinity. Okay, so along this line here, I'm going to be going away from the origin in both directions. Okay, but along the other line, okay, in this direction, I know that I'm going to 0 in both directions. I would always go ahead and plot out the lines first and get the directions correct on the lines, because then it's way easier to draw the lines in after that. Okay, you could see where the other lines go and where the trajectories go. Okay, if you were actually on one of those lines, it just corresponds to either C1 or C2 equaling 0. That's all it means. Okay, so you can actually be on those lines. They are trajectories themselves. That's why I tend to draw them in the same color, but I really want to show you first drawing out the lines, then getting the directions, then getting all the other lines put in. Okay, so those lines themselves are trajectories. They just deal with either C1 equaling 0 or C2 equaling 0. Draw on the directions on the lines depending on what the eigenvalues are, and now you can draw in the rest of the trajectories. Okay, I tend to draw in like 1 or 2 more. So along this line, I know that I'm going this way, and then I turn that corner and I'm going this way. Okay, drawing in 1 more. Okay, I'm going along here and then back up here. Okay, and then you can draw in a couple more over here. You can make that be 1 line and that be another line. As I said, it doesn't have to be accurate. And then these lines, you actually follow it all the way down. Okay, you should never have a line where halfway through the line, oh, I've actually done exactly what I was about to say you shouldn't do. You should never have a line where you end up changing direction halfway through the line. Okay, so whenever you have one of these lines, you should always be going the same direction the entire time. So if I go along this line, I'm going this way, and I'm still, even though I turn that corner, I don't actually change direction. I'm still going along the line. I don't suddenly stop and turn around. Okay, so as you follow that line, you don't suddenly stop, do a 180 and come back the way you just came. Okay, you always go the same direction. Once you start a line, you keep going and go back the other way. Okay, so make sure you don't suddenly get to a point. What I basically mean is you don't have a line where you end up with that kind of a situation. Okay, so make sure once you're on a line, you're always going the right direction. I'll just finish off this one. As I said, if you ever have to sketch these, it doesn't have to be accurate. Just make sure it makes somewhat like some form of sense when you draw it. Okay, so that's what that should look like. Okay, so each one of these paths corresponds to a different C1 and C2. Okay, now there is another situation that you can sometimes come across. And that's when you have complex eigenvalues. Don't worry too much about this situation. What this basically does is, instead of having a situation like we have here, where you can go ahead and plot those lines in, those eigenvectors, and then draw all the trajectories in. There is a diagram, it's on page 310, that corresponds to something having complex eigenvalues. It is not an easy thing to draw. And if I remember correctly, they do actually do this in differential equations. I think that's when I learned it. It was in differential equations. It's more to do with complex eigenvalues and drawing these. Basically, the trajectories now are going to form a spiral, okay? For what you need to know, basically, if you remember when we did complex eigenvalues in 5.5, when you have a complex eigenvalue and complex eigenvectors, remember you can split that real matrix up into one matrix that deals with a scaling factor and one matrix that deals with a rotation. It's that rotational part of it that causes these trajectories to spiral, okay? So any matrix that has complex eigenvectors and eigenvalues, because it's got those complex eigenvectors, when you actually go ahead and draw these out, they're actually going to end up being a spiral rather than a straight line, okay, because of the way that these matrices act. So for what you need to know, that's all you need to know about it, okay? They will spiral. But there is an example, as I said, if you look at page 310, right at the top of the page, they've drawn an example of one of these so you can see what it actually will look like. Again, don't worry too much about it, but they are possible to draw. I'm just not going to ask you to draw them. Okay, finally, the last thing I want to go through is I want to talk through what our next Matlab assignment would have been, because this is where we would have done it. I'm not going to assign it because I know trying to get everyone to get the correct software right now. I know that there's some free stuff that you can get online so that most people could get it, but I just don't want people trying to use different software and stuff and then it go wrong. So I'm just going to talk through it and exactly what you would have done. It is leading off of the last Matlab assignment. If you remember, we looked at the spotted owl populations, where we looked at juvenile, subadult and adult owls and their populations. And then you kept multiplying by A and it would show you month after month what the population would be. Well, and I said to you at the end, like, plot out after so many months or so many years how many owls there would have been. You can do that without dealing with the iterations like we did last time. You can actually look at what's going to happen to their populations by looking at the eigenvalues and eigenvectors of that matrix. Okay, if you remember that matrix A, they have actually written it out for you in the textbook. It's right at the bottom of page 309. They've written out that matrix A that we dealt with, that we were constantly multiplying the population vector by A, and it told us what the populations of each of the categories of owls were the following month. If you look at that matrix, what they have done is they have found its eigenvalues and eigenvectors. Now, you would never have to plot anything like this because it would be in 3 dimensions, not 2, okay? So you have this 3x3 matrix, and what they have done, exactly as what we have done here, is they have gone ahead and found its eigenvalues and eigenvectors, okay? It turns out for this matrix, it has one real eigenvalue and then a complex conjugate pair of eigenvalues. But all of those eigenvalues have magnitude less than 1, okay? So if you go ahead, I think they have said on the following page, on page 310, exactly what those eigenvalues were. It was 0.98, then negative 0.02 plus 0.21i, and negative 0.02 minus 0.21i, okay? To find the magnitude of a complex number, just take the square of each of the values. So take the square of the real part, square of the imaginary part, add them together and square root. And you can find their magnitude, but all of these have magnitude less than 1. So we already know in all directions, okay, whatever your eigenvectors are, you know that xk, that kth iteration, is going to go to 0 as k goes to infinity. okay, because all of your eigenvalues have magnitude less than 1. What does that mean? It means, sadly, that the population would die out, okay? All of the owls would die out. However, it was looking at a specific case for this specific place in California, and it was saying that for that place, that second entry in that first column was 0.18, and that dealt with how many, I think it was subadults went to become adults, or how many juveniles went to become subadults. I can't remember which way round it was, but when that proportion changed depending on the place that you were in, when that proportion changed, it can actually change the whole outcome. So if instead of 0.18 there, you change it to 0.3, so this time 0.3 survives, so 30% of them survive as opposed to 18%. If instead 0.3 survive and you plug in 0.3 in that second entry there, they go ahead again and find the eigenvalues and eigenvectors of that matrix. And it turns out that, again, you've got a complex conjugate pair of eigenvalues, and that complex conjugate pair, both of them have a magnitude less than 1. But the real eigenvector is now 1.01. It is just above 1, which means it has magnitude greater than 1. So in that direction, okay, we know that we're going to be going towards infinity because of that 1.01 having magnitude greater than 1, which would mean that no matter what the other eigenvalues are, there is a chance that now they're not going to die out, because there is a term that is going to go to infinity as k goes to infinity. Now, it's going to go there slowly, but it does mean that you have a steady increase in the population. Okay, so that's where this thing kind of comes into play, is when they deal with real world problems. It's dealt a lot with in biology, epidemiology, and that kind of thing, where they have these matrices. They're normally much bigger than this. They have these matrices that are going to show us how the state of the population changes month to month, year to year. And what they can do by looking at the percentage of how many, in this case, owls survive to go on to the next stage, they can fill in this matrix, and then they can say, okay, let's look at its eigenvectors and eigenvalues. Do these eigenvalues have magnitude greater than 1 or less than 1? What's going to happen to the population overall? Okay, they use it a lot, which is kind of appropriate right now. It's used a lot in disease control as well. I actually did a class when I was in undergrad on epidemiology, mathematical epidemiology, and we dealt a lot with these matrices to see, like, would things die out, how fast will they die out, and mathematical modeling with that. Okay, so it is used a lot in that kind of area. If you do go on to differential equations, which, as I said, is chapter 5.7, where they look at these dynamical systems, but this time in terms of differential equations and how to solve those, that is, again, where it's used a lot. And it can show you, like, a vibration within a system, or how it... they use it a lot with population control as well, with differential equations. If you want to go ahead and look at that, please do. But this is kind of like the basics of it that you need to know. So if you do go on to take differential equations, you now know the basics of what you're going to be covering. But it is really interesting with some of these real world problems and how it can model this stuff in real life. Okay. If you have any questions, please let me know. Or if you just want to talk through some of this or talk through some of 5.7, I'm happy to do that. And I will see you in the next video.